little bit of background on reinforcement learning. I'm pretty sure you guys mostly already know. So usually there is in RL there is an underlying environment which mathematically is called an MVP, in which an agent interacting with the environment, and based on the interaction, it changes the course of action it takes, and it has an objective in mind and tries to optimize. So, for example, you can think of a self-driving car in which it's driving through traffic. It rotates the wheel, and as it changes, the view of the camera changes. So the underlying, based on the action, rotating the wheel, the view of the camera changes. So the underlying state of the world changes. It receives the feedback in terms of the new state and also the reward or cost that it has observed. So for example, you're getting closer to pedestrians, so you want to react to that. Or you have not crashed, so you're at least happy. Based on that, you define an underlying reward, and the agent tries to have interactions with the environment to reach its goal. So more formally, I'm looking at finite horizon reinforcement learning type algorithms, in which there is a horizon, a fixed horizon edge, that the agent is having interaction with the environment. And for any specific horizon edge, the agents observe and underline the state of the world, which I denoted by SH. There is an underlying policy associated with the current step. And we are assuming the underlying policy is a Markov policy because the optimum policy is going to be Markov in this scenario. Then we are focusing on, it can be deterministic or it can be probabilistic, but at this point, I'm just considering deterministic action. So at state H, based on the at time horizon H, based on the state that I'm in, I'm going to take an action AH, receive a reward, which can be random or fixed. And after that, based on some underlying transition probability, which is unknown, I'm going to move to a new state, SH cluster. Okay. Usually, the difficulty in reinforcement learning type algorithms is the unknown underlying dynamic. And here, I'm going to assume that the reward is constant, though all the analysis easily generalizes to the case that the reward is random, but bounded. So based on the interactions that you have with the environment, you're going to see a series of state, action, and reward of the horizon edge. And there is an underlying objective that you're trying to achieve. Usually the objective is to maximize the expected reward that you will see over the horizon. So my goal is to find a policy that will maximize the total reward that I'm receiving. And here, usually, traditionally, the focus is on the expected reward. This expectation is respect to the randomness of the transition probability and not the reward. At least in the setting that I'm looking at. Okay. But in most real case scenarios, this is called risk neutral setting, and most case scenario risk neutral setting has a very important vulnerability. It may experience catastrophic outcomes, rare but catastrophic outcomes. So they expect, in terms of expectation, the performance might be fine, but you may hit the states that you don't really want and you want to avoid them. So there is a extensive and more recent literature that works on risk sensitive setting, which is very important. So for example, in healthcare scenarios or financial situation, that rare events can be very catastrophic and you want to try to avoid. So how would you incorporate that? Usually you change your underlying reward function. And there are many, many different risk sensitive scenarios. You can try to maximize the mean while penalizing high variance. You can try to, instead of this, you can try to look at the exponential cost, which if you only look at the first two terms in the Taylor series, it will be the same as here. And based on whether alpha is positive or negative, you will be risk sensitive, risk averse, or risk seeking. Or you may look at the C-bar as your objective function. In any case, the overall idea is to maximize some underlying objective function. And this objective function might be risk neutral or risk sensitive, and it has different forms. So I have ran a little bit, so keep breathing while talking. So the goal is to find the optimal policy pi star that maximizes some underlying objective J. Okay. Now the question is, well, you are interacting with the environment over a series of episodes, and you want to find pi star, but what is the how can I, what's the underlying metric for comparing the performance of two different algorithms? And usually people focus on the what is called the expected regret. And the regret is how much you regret the decision that you have made so far. So you wanted to find the policy pi star, which will give you some specific value j of pi star, but over the horizon, you have actually picked a policy pi k instead of picking policy pi star. So at episode k, small k, your policy was pi k, which is a random policy based on the observations that you have made so far. And this is going to be the regret that you have observed. Notice that this regret is actually random. Okay? So usually people just look at this expected regret. In some scenarios, calculating the expected regret is going to be very hard. So they also look at pack guarantees, in which basically says that how many episodes you need to run your algorithm till you make sure that the policy, the final policy that you have found, is actually somewhat in a neighborhood of the optimal policy, or the performance of the final policy, the policy you have found is close to the optimal policy. And there's a connection between these two. At least if you have an algorithm that has a good regret, then you can find an algorithm that has a good sample complexity. Any idea how? Right, I can write it here. So, good questions for PhD students. If I have a policy that has a small expected regret, how can I find a policy that has a good performance guarantee? Just pick a policy uniform diagram. Just pick a policy, pick pi k uniformly at random over k episode, because the regretting here is sublinear, then you can get some sort of guarantees. Okay? So at least it is easy to go from here to here, and pack guarantees are usually used in the problems that are harder to calculate the regrets. Okay. So again, we have some underlying objective function, and now we have established what is the underlying metric to compare the performance of two algorithms. So what's the basic trade-off of looking at risk sensitive and risk neutral? Why we change the objective function? There are two questions that actually, when I was thinking about the problem, bogged my mind. What are we really trying to avoid? Right? When you go to the risk sensitive, we say we are avoiding catastrophic outcomes. Okay, but what about rare sample path or bad sample path? Okay. So you can think of it. I mean, these two overlap a little bit. But when it comes to the risk-sensitive objective, you are trying to mostly avoid rare or catastrophic states. You're trying to not reach a state with high reward, with low reward, right? You're trying to avoid those. Okay? But then you're looking at the expected regret because you are only looking at the expected value there, or even if you change your underlying objective function, it is possible that you have a bad run of your learning algorithm. Again, these two are not very completely disjoint. These two are a little bit interconnected, but there is a distinction. So when we are looking at the risk-sensitive setting, it avoids undesirable sample paths and very catastrophic events in the environment. It is mostly related to your environment. Okay. And the cost, if anybody who have done simulation in here and read the papers in here, they know why, for example, almost none of the exponential cost papers for risk-sensitive scenario had a simulation. Because the amount of data you need to make it work is just non-feasible, right? Or the performance, the gap between the empirical performance and the theoretical performance is huge. If you do not, apply any variance reduction technique, if you do not do any of those, the performance is not very good.
You're going to talk about that in the learning phase or the implementation?
No, the learning phase. Implementation, that's easy. So the performance of the learning phase, that's going to be, you need lots of data, and the dependency on parameter horizon H is very huge. Right? So for example, in exponential cost MDP, the dependency on the parameter data, the horizon is going to be exponential if you want to get a good regret. Okay, but for expected value, it's going to be H to the power 3 or 6, depending on whether you're looking at sample dependent or sample independent. I'll also clarify what those terms.
Yes, you already said this, but just to make sure I am following, right? So if you have this like policy that achieves good regrets, then if you randomize over different rounds of your learning algorithm, you are essentially avoiding this bad rounds of the algorithm with high probabilities. That the intuition there.
No, actually no. So when I said the randomized case, is that if I want to find a policy that has a good performance with respect to pi star, okay, that randomization will give you that. Okay, but that's for the case when you are, running your policy and then you want to give me one policy as the outcome. Okay, but however, in most real scenarios, you're in an online setting. You're learning while the algorithm is running. Okay, so your performance usually is associated with the whole horizon that you're looking at. Okay, and in here you might have bad sample path.
And randomization don't avoid those bad samples.
Randomization happens at the end of your algorithm, right? So randomization is guaranteed that is related to the outcome of your algorithm at the very end, right? But regret is a guarantee that you have over the whole K episode that you're looking at. Okay. So I mean, so again, let me put more emphasis in here. In the pack guarantees, I'm looking only for one policy. I ask you to give me one policy that has acceptable performance. Okay, I don't care what happens during this K episodes. I ask you for one policy that has acceptable performance. In the regret, I actually care about what happens during each of these episodes. I want to have a reasonable performance all over the time. Okay? What I'm saying in here is that if you have an algorithm that has a good regret, if you pick one of these policies uniformly at random, that specific policy has an acceptable performance.
Or you are not randomizing at runtime.
It is at the end, yes. I'm randomizing the policy that I give you at the very end of the algorithm.
But you are picking one policy at random. It's not like at each time step
Exactly.
you randomly
Yes.
pick one of the policies.
Yes,
Okay.
yes. It's a guarantee that happens at the very end.
Okay.
But when it comes to the RL algorithm, well, you might have high variance in the exploration area, in the exploration in the exploration phase, which can lead to the bad cumulative regrets. What do I mean by that? So the basic problem here is that we do not understand what is the tail of our regret. Again, what does that mean? That means that, well, you might have a good performance in terms of the expectation of the regret. But what about the tail of the regret? You might have a run, even not high probability, but you might have a run that the expected regret is high, and then the regret itself is high. I do not have any guarantee on the tail behavior of the regret. When you're looking at the expected regret, you're only looking at the average performance of your algorithm. You might have bad runs. On average, you won't see those. But what I'm imposing in here is that what about the tail? What about those rare events that the sample pass that behaves badly? Do we have any bound for those ones?
And this is even when you can choose to punish the variance as one of the three examples. you showed.
Yes. This comes from the regret. So this after you define the peak J, right? You pick J, you already decided to punish the variance of the fluctuation related to the environment. You decided to avoid sample paths that have lots of fluctuations by incorporating it in here. So you pick this as your J. But then now I'm asking, well, you fix the notion of your regret, and your regret might try to avoid sample path related with high values, which is related to your environment. But then you are still looking at the expected performance. What about the runs that have a small probability of giving you bad regret? Right? So we have kind of a algorithmic risk, which is a risk that your algorithm have rare bad performances, and then environmental risk, which is that when there's lots of variability in my environment, I want to avoid those. This is the place that you pick a better J function. This is a place that, well, you try to have an algorithm that not only have a good expected regret, but also have a better tail behavior. Is a distinction between these two clear? Because this is the main idea of the thing. Yes.
Can you replace? Can you work maybe with the risk sensitive for the regret?
Yeah, that's what I'm saying. You may work with the risk sensitive regret. So you are trying to incorporate the environmental risks. Okay, so you are trying to, for example, you may want to. You may decide to pick this as your J function. Right?
No, I'm saying that when you have regret, so you have e to the lambda, yeah.
So,
No,
so
to e to the lambda of the sum or something.
you can look at the e to the lambda of the regret, right? Or the way that I'm thinking about it is that I want to understand the tail behavior.
Yes.
Right? You may say that, hey, why are you looking at the tail behavior? Maybe I prefer to look at the moment of regrets, moment generating function of the regret. That's also valid. So I'm trying to say that these two comes from different steps. One of them is related to avoiding bad states, catastrophic states, that you incorporated in your function J by picking a different notion. The other thing is that, well, you pick your regret, but because still you're trying to optimize the expected value, it may still have bad runs. And that comes from your sample as mainly.
So the background here come from like you are doing online learning, you are learning.
You are doing acceleration, yes, right? So we are in an online setting. I mean, I should have probably mentioned that this is the whole thing. I mean, when you're talking about regret, our notion of analysis is just online. I forgot to say that in online settings. Okay. Okay. And when we started to look at this, we noticed two main things. Almost all the analysis that are in the literature right now, just look at the expected value. And the way that for UCB RL, UCB ITAP analysis it works is that it finds it come up with a bonus function. I mean, we don't know what that is, it doesn't matter. But it come up with an algorithm that guarantees a good behavior for a specific quantile. Okay? So you can say that the probability that regret performs worse than some function that depends on the quantile that you're looking at is bounded by delta. And then you bound the expected regret, but say that, hey, with a small probability, it has bad behavior. So on the event of bad behavior, I assume the regret is the worst possible because the delta I can use my input parameter and I can make it small. On the event of the good behavior, I have a good bound for my regret. Okay. So nobody really looked at the behavior of the regret over the whole quantile, all the quantiles. So what we are asking is this. What is the probability that the regret is greater than or equal to x for all x larger than the mean? I'm not looking at the expected anymore. I want to have a better characterization of the tail distribution of my regrets. And if I want to improve it, is there a way for me to mitigate that? Can I just change my algorithm a little bit to get a better tail behavior? And this bugs me, and this is the perfect mean to describe how I feel. I still have no idea whether this is a deep question or something that everybody had missed. And I'm leaning more toward the deep question because I will just say that, this problem, people have started to look at this problem in the multi-ohm bandit just recently. So the story is that, we found this gap and we were just, why no one has worked on this and why everybody are just only interested in a specific quantile. And then Silo Tejo at a meeting told us that there's a recent paper who have tried to solve this problem for multi-ohm bandit. At the time, we were working on the multi-ohm bandit version. And then we'll notice, okay, we read the paper and then we read the follow-up papers and we noticed that, this is the RL setting is still one of the problem. So we started working on that. So that brings me to what people have done in multi-ohm bandit setting. Okay. And there's a very good understanding of what happens in multi-ohm banding, as long as you're looking at the expected regret. So we already know that in the worst case expected regret, which means that it's a min max bound. So you're considering the worst possible underlying setting that you have. So you do not you're considering the regret over the worst possible parameters, input parameters. And in that case, you can show actually the regret is going to be square root of t. There are algorithms that will have a square root of t performance. And there's a recent instant dependent algorithms by Simchovich, which actually they show you can get off log t, and t here is the number of episodes. So t is the number of episodes of one multi-ohm bandit algorithm. And okay, everybody knows what is a multi-ohm bandit? Okay, let me just remind you. So in a multi-arm bandit, there are multiple arms, and each of them have its own underlying reward. And I'm trying to find the best arm, but I do not know the expected performance of any of the arms, so I just pull the arm, receive the reward, and then keep searching. And over the time, I want to maximize, I want to get closer to the best arm while maintaining a good performance. And my performance is usually going to be in terms of the regret when we are in the online setting.
So it might be in stochastic bandits, so these rewards are generated IID. We
Yes,
each one
every
have to
time,
serve
yes.
To IID.
Yes, yes.
How is PyStar determined this? Is it
Uh,
just choosing the like correct arm?
Yeah. Yeah, the pi sign here is just best arm. Yeah. So your regret is going to be, the expected value of the best arm minus whatever arm you picked at each expected value of each. I mean, the mean of the arm that you picked at each episode. And there's an instant dependent case, which so by instant dependent is that the bound you're going to get is going to have a term which is related to the MDP, which is related to the underlying bounding problem that you're looking at. And usually it's going to be the difference between the performance of the best arm and the second best arm.
And
So this regret term doesn't have any parameter related to the underlying bandit. This regret in here has 1 over delta usually, which delta is just the difference of the performance of the the best arm and the second best arm.
so these are weak regret, is that right? You're comparing it against the best single action choice, right?
Yes.
Policy.
Yes.
Just the one with the highest mean.
Yes, yes.
Okay.
We are comparing with the best choice of it.
Yeah.
Okay. And Long Robin said that, well, in this case, you should have the off log t like this. You cannot do better than that. Okay. And so we have the best performance for the instance dependent regret. But what if you look beyond the expected value? And there's a series of paper that shows actually the algorithms that do optimally for they're actually the results in here are very strong and very recent. So we have 2024 paper and 2022 papers. These are the main papers that are up there with theoretical proof that says that if you go for optimal arm, you will have bad tail behavior. Okay. Okay. So first, this is actually on 2009 and 2012. This shows that good algorithms have bad concentration. You have a good expected regret, but the concentration is bad, right? But then there's a recent paper. This is a main breakthrough that happens 2-3 years ago. It says, I think it went to arXiv in 2021, but the paper is published in 2025 or 2026, and it has already more than 10 variants. Like they have corrected and submitted and corrected and submitted. It's in OR now. It's a fragility of the model assumption. So they show many interesting results. They show that if you go for the algorithm that gives you optimal expected regret, the tail is going to be polynomial. So the tail is going to be 1 over t. Okay. So if you want to do best regret, there's no way for you to have good tail behavior. The other thing that they actually analyze is the moment of the regret. So if you're interested in the second moment of regret, or third moment of regret, or kth moment of regret, so regret to the power p, it's going to be polynomial again in terms of the
So the reason behind it happening, so all these algorithms, ultimately they're aiming for, in the long run, playing the optimal arm infinitely often, right?
Yes.
Now you lose, your regret is coming from exploration.
That's
You
right.
still have to explore. So the bad tail comes from the likelihood of actually latching onto at a suboptimal arm, or it is coming from
Bad sample path.
it's bad some. So basically, you're selecting a suboptimal.
Yes, yes. So it comes from the fact, for example, that initially you selected good arm for a long period of time, but the performance that you see from the good arm was really poor. So it will take you much longer to recover, right? And those will end up being in the tail of the distribution.
And
And again, the goal is to maximize the expected value. That's also the
yeah,
other.
no, I get it. And then this critical constants we always have, which is the difference between the best and the second best.
That's
How
delta.
does that come into these results?
That's a very good question, and I do so in regret it will be in the denominator, it will be just delta, and in the tail behavior. It's a very good question. I'm not going to make a guess because I don't remember. It's a very good question. Yeah, I don't remember exactly what happens. I mean, we'll see in our case, but I don't remember exactly where it will appear in terms of the promotional bandwidth. So if you go for whatever that maximizing the expected regret, the tail behavior is going to be polynomial. So it's going to be decaying with 1 over t. The other thing is that, well, if you look at the moments of the regret, so instead of looking at the expectation of the regret, look at the expectation of RT. Let's look at the expectation of RT to the power t. Okay, then you can show that the tail is the expected value actually is going to be polynomial in terms of t. It's going to be t to the power p minus 1. Okay, for again expected regret maximizing algorithm. And the other thing is that it is very fragile with respect to the problem setting. So for example, let's say that the underlying distribution of your arm, you run your algorithm in a setting that the underlying distribution of all the arm are Gaussian with unknown mean, but some specific variance. You learn some algorithm, now you shift it to another setting in which still all the performance regard distribution of the arms are Gaussian, but the variance of that has changed just a little. The performance also going to be catastrophic. So it is fragile in t-distant sense. Okay? But what we are really interested in is this one. That the regret, the tail of the distribution is actually going to be 1 over t. Okay? And again, remember, t in here is the number of episodes that are running my multi-arm bandwidth algorithm. In the very interesting follow-up work by Senchelevi and co-authors, they ask a different perspective. They say, okay, what if I want to improve the performance of the tail? Can I adjust my algorithm a little bit to make sure that I have a nice tail behavior all over the place? And they actually find that, so they say that they do more exploration, more gentle exploration to make sure that they have better estimation, so those bad events won't happen as much. And so instead of doing log of the appearing in the bonus function, it will be t to the alpha appearing in the bonus function. So it's going to be a little bit more aggressive, and alpha is smaller than 1, so it's going to be more aggressive exploration. You're assigning more bonus to states that you don't have enough information to, so you're more incentivized to search those arms. Okay, and then they show that in that case, the tail goes from 1 over t to e to the minus t to the alpha. They actually did much better. They in the final paper that came out last year, they show that if I want to get a specific performance of regret, I cannot do better than a certain amounting tail. So if you want to maximize expected regret, you cannot do better than that. But if you want to maximize a certain moment in regret, you cannot do better than in the tail. So if you want to maximize if you want to get the best expected regret, you cannot do better than polynomial tail. But if you want to relax the expected regret by amount of t to the beta, then the performance of the tail will change to t to the some alpha for best you can ever do. Like they find a balance between these two notions: the performance of the expected regret and the performance of the tail distribution. So you tell me what the tail distribution you want, what guarantee on the tail distribution you want to have. I can say what's the best expected regret you can get. You tell me what performance of the expected regret you want to have. I can tell you what's the best tail distribution. So they found a Pareto frontier of the behavior between the expected regret and tail of the regret. The problem is fundamentally different, more difficult in RL setting. Well, mainly because in RL, what you see is not IID anymore. I mean, it's underlying MDP, So the transitions are dependent on each other. So the problem is going to be more important. So in regret, in the Montion bandit, the unknown in the stochastic Montion bandit, the unknown part is the reward that you're receiving. So at each time when you're pulling an arm, what you see is going to be IID. In here, the unknown part is mainly the transition that happens after taking an action. And whatever happens in the first, I don't know, small h episode is going to affect the sample pass that you'll see in the future episodes as well. So that there are lots of work that generalizes the idea of the Montion bandit to here, but the technicality usually is much more different. I mean, the basic ideas might be the same, but the technicalities are really different because the randomness that you're not aware of is a different type of randomness. So it's dependency in the transitions that you see over the horizon.
Just quick question, are you like between episodes, are you just resetting the initial condition or are you continuing with it?
So
So like then why episodes are not?
I use the term episode. I mean between the time horizons.
Yeah.
Yeah, you're right. Yeah, I know. Between episodes, everything resets, but but the actions that you take in the first small edge horizon is going to affect what you see in the next steps. Thank you.
There's a question on Zoom. In the real world, a lot of problems are constrained. How does this apply to constrained cases, especially those safety critical systems with?
So it's a good question. We are dealing with a much more basic scenario. Usually, the way that expected regret work in the constraint case is that you find some sort of, you look at the Lagrangian, you try to optimize the Lagrangian, right? But for the Lagrangian to work, you need to make sure certain underlying condition happens. What was the name of it? Oh, I forgot. It's a very famous condition that if it holds, then Lagrangian, you have a strong duality, but there's a specific condition, I forgot the. Yeah. So you have strong, and if that condition holds, you have a strong duality. And the way to prove it is that they actually look at the state action distribution, and they show that the space of the state action distribution is convex. And then if you have the static condition, then a strong duality holds. So if you run your algorithm for the Lagrangian, if you just run the value maximizing the UCD type algorithm for your Lagrangian, it gives you a good performance in terms of the expected regret and the violation. Then there's this question of usually that when people are looking at the violation, they usually are just looking at the performance difference instead of looking at the performance difference plus, meaning that, well, if I'm not violating, I do not care how much I'm not violating. I only care if I am violating with the amount of that I'm violating. So that will change the analysis a little bit, but the basic idea is that you show some sort of a strong duality, and then you show that UCB type algorithm work in that scenario. So my guess will be, well, you can ask the same question in terms of the tail behavior of the violation and tail behavior of the regret, and all you need is going to be some sort of strong duality and probably more tedious algebraic work to get the result. Any other questions? Okay. So let's look at let's fix the problem formulation. So there is an underlying pi star. So we have a state space S and action space A. We are assuming everything is finite here. There's an underlying transition pi star, which we are not aware of, and we are assuming the underlying reward function is not random. So if you give it a state and action, it will just spit out a number between 0 and 1. But the analysis, generalizes to the case that this is random as well, with much more tedious work. Okay. There's no intuition. It doesn't add anything to the intuition, so it doesn't work. We're looking at the instance-dependent case. And remember, when we are talking about the Montion bandit, when we are saying instance-dependent case, we're talking about the best performance. The regret you're going to get is going to be in terms of the difference of the performance of the best arm and second best arm. In RL, it's going to be the difference of the performance between the best action, VS star is going to be the value function associated with the best policy, and any other action. So second best action would be if I maximize over all the actions that are not optimal. So this this gap basically tells you if you would have followed the best policy, this is what you would have get starting from episode H and state S. But you decided to take the action A and then follow the best policy. This is how much you deviate from the best outcome. So when people are talking about the performance of instant dependent regret in RL, it's usually categorized with the quantity of the gap between different states of action. And usually the bound is going to be in terms of the minimum of this quantity over all H, all S, and all A, as long as A is not the best action. Because if A is the best action, this quantity is going to be zero. Okay? And again, because we're in this finite state, finite action, this minimum is bounded at equal to. And this is the gap started exactly. We minimize it over all the states, all the action, all the horizons, as long as my action is not the best action associated with this specific state. Okay. So, how does the algorithm work? You pick a policy at each episode. Based on the policy that you pick, you make actions. Based on the actions you have made, you will see new states. And over the K episodes, you will have different sample in the XYK. I'm so not used to use this, and I keep going there and just something. And usually the performance metric is going to be just a regret. Expected regret. This is exactly defined as we talked about. So this is the performance of the best policy. This is the performance of the policy by K. Okay. And we want to have an algorithm that have a good expected regret. You know, the best expected regret is going to be log of K, order of log of K divided by delta with many more constants. But we want to have a good expected regret while having a good tail K. So what's the main result? So our main results is it comes in two shapes. We look at the UCBBI and optimistic Q-learning algorithm. In the UCBBI, we look at both K dependence and K independence, or K dependent case and the case that it is anytime, or to be more specific, consider a scenario that I will tell you how many episodes you are going to run your algorithm, and I expect a good performance, to the case that, well, I do not tell you how many times I'm going to run the algorithm. You just keep running the algorithm. So you don't know what is the capital K. Okay, so this can be thought of as a case that you have a fixed number of episodes that you want to run your algorithm. This can be thought as a case that you want to run your algorithm for 100 times today, and tomorrow you come and decide that, well, I want to run it more. So still you can use the result that you have right here to continue, because this K was never fixed. Okay?
So what is this lowercase k?
The episode that you are at.
Oh, I
So this capital K is number of episodes. This lowercase k is the episode that you are at currently. And in the expected maximizing regret, these values are log K. This is log BK. Okay. And we also look at the optimistic Q-learning algorithm. This is a model-free algorithm. So in the model-based algorithm, what happens is that, well, you estimate the transition probability using the empirical estimation. So you see how many times upon taking action action A at a state S, you will go to a state S prime, and that will be your estimation of that specific transition probability. But then you add a bonus to your reward function. So you see that instead of the reward to be R plus a bonus function, which these are the bonus function that you will add, and you will run your algorithm. So in here, you are actually estimating the transition probabilities, but there's a model-free case as well, in which you are not estimating the transition probability, you are interested in Q, the Q value, and you keep updating that based on the value that you have seen so far. So this is a synchronous case, to speak. So you pick your model, and then you solve the Bellman equation. You just do dynamic programming from, say, capital H, and you try to solve it backward. Here, you are not estimating the here you are not estimating transition probabilities anymore. You take action, you take every state, you take an action, and based on the values that you see, you update the Q function associated with what you saw at that specific point. So here at any time, I'm updating only the Q value associated with the state and action that I have seen at this situation.
Are these both for finite states?
Yes, finite state, finite action. And in here, this is going to be our bonus function, and this n in the model 3 case is going to be number of times that you have seen that specific state and action pair. This t in here is going to play the same. Number of times that you have seen that specific state and action that you're plugging in the bonus function. So what we have really changed is that, as Simchi and Lady suggested in the multi-band case, what we have changed is that instead of having log k in here, we have replaced log k with k to the alpha. And we asked the question, what will be the performance of the tail? And this is what we have. So the tail is going to be a sub-Gaussian term plus a sub-Weibull term. My algorithm only have one parameter alpha, so this gamma is any arbitrary parameter that you pick between 0 and 1. It comes into the picture when you are looking at the it's just an algebraic analysis. So so what you would do is that you pick the lambda that will give you the best performance here. In here, and give the desired performance in here. So before going through the proof of this, I want to highlight a few points. There is a transition happening between these two because this is a sub-Gaussian term. This is a sub-Weibull term. This term, as you see, has k to the alpha. If you're looking at the case that you know the number of episodes you're running the algorithm, or k to the gamma alpha, if you're looking at the case that you don't know the parameter of algorithm. Okay, so this has nothing to do with x. Okay, but this term is related to the x, so it is sub-Gaussian. This transition between this sub-Gaussian and sub-Weibull term happens at a certain point. I will emphasize on that in the next in here. But the main intuition is that this is related to the probability of bad events happening in RL. If you're familiar with the RL analysis, you know that usually you want to have a certain guarantee on the performance of the sample paths that you have seen for the transition probability. Right? The analysis usually go that you want to have make sure that a good event is happening, so the estimation of the sample paths are close to the sample paths, or close to the true probability, and then you do our analysis there. Okay. If that is not happening, usually you cannot do anything, and that's a technical barrier that we have. We do believe that you cannot get rid of this term. Even in the multi-arm bandit, when I show you the tail doesn't extend up to the capital T. It goes up to a certain point. Yes.
So what is bounded again?
So this part comes from the probability of the good event.
I'm asking like the reward you get is a deterministic reward?
Yeah, the reward is deterministic. It is the transition probability, right?
Yeah, but then given like absolute like horizon H, your reward should always be bounded, right?
What should be bounded?
The reward.
The reward is always bounded. That is not related to that. It
Yeah,
comes
so
from
then if X is larger enough, then this probability.
no, X is not going to. I'm not going to push X up to. I'm not going to push X up to K.
Okay.
X goes up to a certain point, right? It starts from the mean. It goes up to a certain point. Up to this point, that sub-Gaussian term is the dominant term. After this point, the sub-Weibull term will be dominant, right? So up to a certain point, this will be after the mean, and this is going to be almost the mean, right? This is the mean. So after the mean, up to a certain point, the sub-Gaussian term is dominant. So you will have a decay up to a point that these two terms will become almost equal to each other. So then this will be the dominant term because it does not depend on X and it doesn't decay with X. Okay? And it is given by K to the alpha. So it is sub-Weibull, it's not sub-Gaussian anymore. So if you look at the tail up to a certain point, you have a sub-Gaussian behavior, but then you have a sub-Weibull behavior.
So what's the rationale if the gap appears in the denominator? If all the actions would give me almost the same cost, my regret would be almost zero.
No. The regret comes from the transition probability. You do not know the underlying transition probability. This gap is
It's for the value.
for the, but then when you take an action, the performance you see is going to be different. At any point, you are not going to take an action that is the best current performance, will give you the best current reward at this point. You need to think about what's going to be the reward that you're receiving from this point onward.
Yeah, but suppose that all the actions would give me the same cost,
Yeah, then there's nothing,
up to some small
then
epsilon.
this quantity will be always zero.
Correct, but then
if-
it's be
if-
almost zero, and if it's almost zero, the regret is going to be almost zero, no?
So, if you, okay, I mean, again, we need this gap start to be positive.
Yeah, the one for epsilon would be large, but the regret itself would be small.
No, it's log over epsilon log, right? So the log will lead to like a gap small usually is large.
It would give me a larger regret.
Or in instant time. It continues to use sometime.
Yeah, you can, so there's when the gap between terms is very small, it is so hard for you to distinguish these two from each other.
Right.
So you will spend more time taking the suboptimal action, if that's what you're
But
asking.
it would be almost zero, I mean, the difference between the cost, no?
Yeah, the difference with the cut will be almost zero, but then, again,
So the regret is not that efficient in such cases.
but again, we are optimizing for the value of, let me bring the life and Robin case. Yeah, we are optimizing in terms of the number of episodes. We want to get best performance in terms of the episodes.
Okay.
Right? I want to make sure that I want to get the best performance for the term that has
The
E,
number.
right?
So the gap is the equivalent of that delta in
Exactly. Yes,
bandit
yes, yes,
literature,
yes.
okay.
If you would have been happy with linear regret in terms of T, we could have avoided one over X, one over gap now. So again, this is a technical issue. We do not have any solution for it. And we do strongly believe that we cannot escape from it.
So I have a question, so if we view the IL from each policy as an up, we can use the multi-unbanded without.
We do, so we are trying to use that as for the lower bound. I mean, this is not in here, but we are actively working to derive a lower bound for that. So you can actually think about it as you can combine the transition with the value of the reward to get a multi-unbanded type algorithm.
But what I'm saying, like, I just view each policy as an up,
Yes,
right? So
Okay.
It's become a multi-unbanded form.
yeah, but then the constant you will have is going to be exponential in terms of the.
Yeah, that's how I'm asking,
Yes.
okay.
So one other thing that we have in here is that if you replace this k alpha with log of k, this is exactly what the best expected regret would be. So we want to match the constants that I have here in the optimal regret.
It's like the state action dependence is very much worse.
Yes, if you do that, the state action dependent will be much worse. Promise not false. And I have not talked about the sketch of the proof at all. But we have a short threshold. So I'm going to just give you the results again. Up to a certain point, we have some Gaussian behavior in which the performance is coming from the martingale noise that you will see in your sample path. After a certain point, we have a subwave behavior, which comes from the probability of bad events. The probability that the estimation that you have for the transition probabilities are completely off. Okay. So you can think of it, I mean, if I want to loosely talk about it, if my bonus function was log k, instead of k to the alpha, I would have had log k. Okay, then this quantity would have been e to the minus log k. So it would have been 1 over k. Right? So polynomial, it's not exponential anymore. And in that case, this transition will also happen, it will happen to be at the very point, so there is no transition between these two. For that, we need to go more in the detail of the session. So you won't get, if I put k to the alpha here with log k, this regime will disappear. So you have the expected regret, and the moment that you pass the expected regret, you will just drop into the polynomial of k. This is still a conjecture, we have not proved that yet. And that is short, we have not proved that it is short. And we have similar result for the Euler, optimistic Euler. Well, I'm going to skip the proof, but the only thing, I mean, the only part that I want to highlight in here is that there are two types of analysis. There's a max mean regret type analysis. There's an instant dependent regret type analysis. In a max mean regret type analysis, that usually in UCRL2 algorithm type analysis, you usually define a martingale and then you bound the you get the function f using a martingale noise, and you match that with what you get with the probability of the bad event. In the instant dependent type analysis, you will assume the good event is large enough so that everything is almost constant, or you can estimate everything almost constantly in there. So the main challenge was to combine these two analyses to make sure that even if you are looking at a gap-dependent analysis, we'll still have some underlying martingale noise, so that we can get the sub-Gaussian tail when that martingale noise exists. So in the process, we came up we came up with a different analysis for instant dependent, which we then use and generalize to apply to our app. Future work. Almost everything here is open. Thompson sampling, why you're doing optimistic auto, says why you're not looking at Thompson sampling, why you're not looking at Bayesian learning. What are the tail for those? I don't know. What are the moments? I have no idea. Moment generative function, still unknown. What is the Pareto frontier? If I want to get this, if I want to sacrifice expected regret up to a certain degree, what's the best tail I can get? If I want to get a certain guarantee on the tail, what's the best regret I can get? I still don't know. It's a very fresh problem, and we just have started to looking in this problem. And again, your takeout should be, in my opinion, is that you have two types of risk. You have algorithmic risk, which happens after you have an objective function, and you may just have bad sample pattern. And then we have environmental risks, which says that, I do want to specifically to avoid certain states that have catastrophic. This is related to the choice of the objective function. The algorithmic risk is related to the tail behavior. Thank you. Yes.
I want to make a comment and also a question, right? I think that there's third risk. So like after you do the online learning, and then if you want to pick a policy, I don't think uniformly randomly pick a policy is the best.
No.
The risk is very high. If I pick a bad policy, that policy always be bad.
Yes, yes.
So in terms of that, any comment on how to pick a good policy?
So what you're proposing is that, well, I'm not happy with PAG guarantee.
Yeah.
Right. Say that I do not want to have a PAG guarantee. I do want to have a higher moment type guarantee.
Yes.
Right. Then that means that you're picking so first off, first count would be, well, the idea of going from here to here is that, well, if you have a good algorithm with a good expected regret, you can get a good PAG guarantee for it. Right.
Or randomly set.
Well, yes, for example, but if you have a good algorithm for expected regret, and instead of PAG guarantee, I replace it with something else, with second moment behavior, with third moment behavior of this distance, right? Instead of having just the probability being this being smaller than that, what if I want to be the expected value of the second moment of this to be smaller than certain quantity, right? This is the same question kind of that they answered in the same question that they answered in the fragility paper, which says that if you pick the algorithm which optimizes for expected regret, now if you look at the moment, the second moment, the third moment, the peak moment of the regret, then the performance will be terrible. It will be polynomial, right? It will be t to the alpha minus 1 over t to the p minus. It will be in terms of O of t to the p minus 1. Okay, so it will be sublinear, but still, it still will be really bad.
Yeah, I guess I'm asking slightly different because I don't want to uniformly randomly pick a policy.
Yes.
What you are arguing still, uniformly randomly pick a policy from K policy.
Yeah.
What's is there any way to pick a better policy?
So where I was going at is that I believe if you want to change this, picking a policy that will give you good regrets may never, you might not be able to pick a policy that will have good performance. That's what I mean.
Thank you. High level question. I don't know if this is relevant at all, but this has a little bit of the flavor of this bias variance trade-offs in static learning problems. Is there a relation there, or?
We have not explored it, but you're absolutely right. So in practice, people use bias variance analysis to make sure that your behavior is a little bit better. This is definitely related to that. But we have not looked at what would the tail look like if you try to run a bias various check modification.
I'll ask the last question.
Yes, of course.
So Kate, so here you. So how significant it is, this is for finite horizon.
Yes.
A lot of the Bender results is a infinite horizon that you have uniform time bound, you know. How much would this be?
We have not looked at, so this is one of the, right? Extension to the infinite horizon time case, or extension to the case that you have a stopping time for the horizon, right? We have not looked at that. I'm not going to make any assertion about it.
Well, let's take this speak. Thank you all for coming.
Thank you very much.
Very nice talk.
Excellent.
Yeah, I'll talk to you more.
Yeah, yeah.